Hello, this is Jack Jackson. We're going to be looking at arithmetic sequences in this lecture. This lecture is going to be divided up into three different videos, one PowerPoint presentation for all three videos. Now, this assumes that you've gone through the introductory exercise that's called the Minds On inquiry-based active learning tasks on arithmetic sequences. Actually, it's on both arithmetic and geometric sequences. But this video will be talking just about arithmetic sequences. We'll come back to talking about geometric sequences later. So this is closely related to part of that project, about half that project. Now, if you haven't done that, just stop this video now, go back and do that, and then come back. So our basic outline is we're going to start with recursive relationships and obtain a physical representation, a table, a recursive formula, an explicit non-recursive formula in a couple of different forms, a graph, and a dynagraph. And so we're going to start this with, we're going to have basically two tasks where we do this. This first video will be on the first of those tasks that deals with some seating arrangements for a concert band. And the second part actually is directly related to your project that you've finished about arranging blocks. And at the end of the second part, we'll kind of summarize what we've learned by looking at these two tasks in detail. Then we'll come back in our third part of the video, our third video that's over this, and it will be talking about some applications and problem solving. One of the things we'll be doing there is starting with, we have a series of things starting with one of these representations and finding all the others. And then we'll have a series of real-world applications and problem solving where we put this into use in real-world problems. In fact, let's start with a real-world problem here. So suppose that there's a concert band, it's setting up chairs, and it's going to put them in a semicircular arrangement centered on the conductor, and there'll be 5 seats on the first row. And after the first row, each subsequent row has 3 more seats in the previous row. So if there's 5 in the first row, there's going to be 3 more in the second row, so that would be 8. And then 3 more in the next row, and 3 more than that in the next row, and so on and so on and so on. And this band has enough people to make up 12 rows made up in this fashion. And we're going to try to investigate how many chairs are on each row. And so we want to look at this situation and represent it in different ways. So first thing we want to do is actually draw a physical representation of the actual layout of the chairs. And then we also want to write down a recursive formula for n, which is the number of chairs in a particular row, as a function of r, which row we're on. So we want to make a table of values where the input is r, the row number, and the output is n sub r, that's n of r. Remember, we use subscripts when we're doing sequences instead of the parentheses thing. But that's n of r, n sub r, which is or just n, which is the number of chairs in row r. Then we want to write an explicit non-recursive formula for n as a function of r. And we want to make a dynagraph for this function on graph paper. That's basically just your arrow diagram, but you put your your data points on coordinate axes, parallel coordinate axes. And then we want to just use a regular Cartesian graph, what we normally think of when we say a graph for this relation. And of course you want to make good use of graph paper, particularly for the dynagraph and the sequence and the Cartesian graph. And so I'm going to leave you to this task. Press pause, work on this a few minutes, and come back and check it out. So here's the basic arrangement. Now I've got a geometry sketchpad sketch that goes through this a little bit at a time, and you have notes here. I've made screenshots and so forth here, so we can so you'll have notes on this. But let me actually get out of this PowerPoint now and go to this sketchpad sketch called Arithmetic Sequences. By the way, I will post this sketch on the Blackboard site, but realize that to run this sketch you need to have one of two things. You either need to have Geometry Sketchpad or you need to have a Sketchpad viewer. There is a free viewer for Geometry Sketchpad for the iPad. And so you can download that viewer and open this if you have an iPad. If you don't, then you need to put a program on your computer. I think it's around $30 or $40 for perpetual license for Sketchpad. This is need Geometry Sketchpad version 5. You can get a student version for around, I think it's around $40 actually, and that lasts forever. You can also get a license, I think is good for a year, for $10. So if you want to just spend $10, and you can get that downloaded directly from Geometry's Sketchpad. Just do a search for it, and you'll be able to find it. And you can download that. That is optional. You don't have to do this. So this will be found down below the exercises, the MyStatLab, or MyMathLab, excuse me, exercises for this unit, or for the directions to go to MyMathLab. And so remember, anything below that, like the Khan Academy videos and other internet resources, are optional. So you can open this up if you want. But anyway, you've got this video to see what's going on. So here's our seating application. And let's see if this is the same thing we said. We want to start with 5 seats and then add 3 each time. And I have this set up, it's dynamic, so the N1 is how many seats are in the first row, and the M is how many we're adding each time. So let's take a look at what we have. So there's our first row with 5 seats. Alright, how many are going to be in the second row? Well, we're going to add 3 to that, so there's going to be a total of 8 in the second row. Okay, we'll add 3 to that to get 11 in the third row. Okay, that does count out to be 11. 3 more, we'll put 14 in the next row. And how much for the next one? Yeah, 17. And then 20, 23, 26, 29, 32, 35. And the 12th row, which is their last row, will be 38 seats. Okay, so we have those 38 seats, and there's the 38 in the last row, and so each dot there represents a seat. So there's our representation. Now we want to find a recursive formula. Now remember, a recursive formula says you need to have 2 things on a recursive formula. You need to tell where you start and then how you get from one to the next. So you need to know what your initial output is. So that's basically this statement right here, that N1 equals 5. That's going to be our first step. We need to put that down, and then we need to know how to get from one to the next. And of course we get from one to the next by adding 3 to the previous output to get the new output. So we start with 5, and to get the N sub r, the N value for any row, we take the N value for the previous row, r minus 1, and add 3. Let's make sure we understand how this works. Okay, so suppose we want to find N sub 5. So what do we need to do? We take 5 minus 1 is 4. We want to find the N that goes with row 4. So find N sub 4, which is 14 seats, and then we add 3 to that to get 17. So this is just saying the same thing that we just did here. Add 3 to the previous output to get the next output. But that alone doesn't define it. We have to tell it where to start. We could start many different places. For example, I could start at 2 here and still add 3 every time, and it's still the same recurrence relation, but it's a different sequence because we started at a different point. Okay, let's go back to the one that we were on, which is a 5 here. Okay, so notice this has a general form of N1 equals some number, and N sub r equals N sub r plus N sub r minus 1 plus some number M, where r is bigger than 1. So this N1 here on the right and this M on the right are specific numbers, in our case 5 and 3, or whatever I have in these boxes right here, which is 5 and 3 in this case. So there's our recursive formula. Next we want to find a table. Okay, so basically we have a table here. Notice that our inputs are just the row numbers, 1, 2, 3, 4, 5, and we have the outputs here. So let's look at the table. Now, if we look at it, this is the numbers that we have, and I extended it all the way out to row 17. They're really this particular band only has 12 rows, but we could extend the pattern on, well, really forever if we wanted to. In the context of this particular problem, perhaps it's not supposed to be extended, but in other contexts, maybe it extends on out, perhaps even forever. Now, if we look, how do we find these? To find the 8, we said the 5 plus the 3. To find the 11, we took the 8, we back up to find, again, using this recursive formula, to find n sub r, so if r is 3, to find its n, we back up 1 to 2, so r minus 1 is 2, find its n, which is 8, and add 3 to that to get 11. So these tables look like this would be r, this is r minus 1, this is n sub r minus 1, this is n sub r. So that's 8 plus 3. Add 3 to that, 11 plus 3 is 14. 14 plus 3 is 17. But let me show you another way to look at this. So the big question now is, how do we take this and get an explicit formula? You know, if we just stop there, I could say, okay, what if we went out to the 100 rows? What would be, how many would be in the 100th row? Well, we could do it this way, but we'd have to do it one row at a time. Is there another way to do this? Is there a shortcut? Well, the key is this. Notice that we started with our 5 and then we added 3. And to that 5 plus 3, we added another 3. And to that 5 plus 3 we added another 3. And then added another 3, and another 3, and so on. I don't have them all written out here, but I've got them written out for a while. So if you look at it, we could write all of these numbers as just 5 plus a certain number of 3's. Well, let's think back to the beginning of our course. What is one way we could write repeated addition? Think back to elementary school or to our first lectures in this course, and you'll remember that that's multiplication. So we can say this is 1 3, so that's 1 times 3, or 3 times 1, plus the 5. This is 2 3s, so that's 3 times 2 plus 5. 3 times 3 plus 5. 3 times 4 plus 5. 3 times 5 plus 5. Then this would be 3 times 6 plus 5. This would be what? 3 times 7 plus 5. So notice it's just 3 times some number plus 5. So how does the number, the first number is 3, that's what we're adding every time, that's the m. The last number is the plus, well, whatever this n1 is. But how does the second number in parentheses compare to the input? Well, if you look, every time it's 1 less than the input. So, what's our formula? Our formula says, take 3 times r minus 1 and add that to 5. So in general, if we generalize that, n sub r is m times r minus 1 plus n sub 1. Now I can also take this and use the distributive property, make this 3r minus 3. Negative 3 plus 5 is 2, so I could write it as 3r plus 2. Now where does 2 show up in the table? Well, it really doesn't. I mean, I guess it does for an input here, but it doesn't for an output. But if we were to extend our table back 1 and look at a 0th row, like if they were going to add an extra row of chairs in the front and call that the 0th row, how many would be on that row if we keep the same pattern going? Well, notice going this way in the table, we're adding adding 3 to the y's, or the n's, the outputs. When we go the other way, when we subtract 1 from the input, we subtract 3 from the output, so that would put us back at 2. So we can interpret this 2 as being the n sub 0, which would be the number in the 0th row. Now it depends on the context of the problem whether there really is a 0th element or not. Sometimes we have our sequences start with a 0th term, and sometimes we only start with the first term. In this particular context, there is no 0th row. There's only a first row, but we can still interpret this as what the 0th row would be if we were to extend the problem back. And it still works. We just define n sub 0 then to be 2, and it is 3r plus 2, or m times r plus n sub 0 to get n sub r. And that formula still works. Put in 1. 3 times 1 is 3, plus 2 is 5. Put in, let's skip over here, 8. 3 times 8 is 24, plus 2 is 26. Put in 100. 3 times 100 plus 2 is 302. Now we can easily find what's in the 100th row or the 1000th row, and we don't have to figure out every output along the way. Now sometimes when you see sequences listed, you'll just see it listed this way: 5, 8, 11, 14, 17, 20, 23, etc. And so in other words, the inputs, the x values, the r values, whatever the input values are called, those are left out. Well, why? Because they're automatically 1, 2, 3, 4, 5. Or they're 0, 1, 2, 3, 4, 5, depending on the context. In this case, they clearly start with 1. So sometimes we will leave that out. Okay, so there's our table, and there's our non-recursive formula. Now how about a dynagraph? Let's do that next. So let me hide some things here and pull up the dynagraph. Okay, and so in a dynagraph, if it's a sequence, it will have it will graph x's at 1, 2, 3, 4, 5. Let me see if I can. I want to adjust this just a little bit. To do this, I need to do that. Okay, so now I don't have exactly the same scale on both, but I can use this. So here, notice that I have an input for 1, 2, 3, 4, 5, 6, 7, 8, 9, and they go on forever. I've only have them worked up through 12 here, which actually in the context of this problem may be all that really matters. And notice I'm the change in r, the delta, this triangle, is a capital Greek letter delta, which stands for the difference in or change in r. So it's the difference in the r. So 2 minus 1 is 1. That's what we're saying here. Or 3 minus 2 is 1. So it's always 1. We're always going up by 1. In other words, we're adding 1 each time on the input. Well, what do we do on the output? We're adding 3 each time. So notice that the inputs are evenly spaced, but the outputs are also evenly spaced. They go up by 3 each time. So from here to here is 3, from here to here is 3, from here to here is 3, from here to here is 3. And we can clearly see, of course, that this is a function, a one-to-one function. It's a sequence. We can see all that by looking at the graph here. And we can also tell it's arithmetic because one thing, the structure we see is that we're going to the right the same amount each time here. So in other words, when we add add 1 to the x, we add a certain number, in this case 3, to the y. We use those letters. Next, let's look at a Cartesian graph. And before I do that, let's hide this. And what I want to actually do is stack the chairs. So let me see if you understand what I'm doing here. So, for example, right here, in this first row of chairs, there are 5 chairs. So instead of arranging them in a circle like this, I'm going to stack them up. And so we see the red dots here, 1, 2, 3, 4, 5. The yellow dots control the scale of this. Okay, the blue dots in the second row, how many are there? Well, there are 8, and so you'll see them here. 1, 2, 3, 4, 5, 6, 7, 8. So there's still a dot for every chair in this particular representation. Okay, now we can see all of them. And so forth. So you can get a good look at the representations here. Now, of course, if we want, we don't have to put all these dots. If we just use the top dot, that of course that gives us our Cartesian graph like this. The yellow dots and this black dot are not part of it, just these other colored dots here. So there's definitely an interesting pattern there, right? So let's put this back for a second. And so notice if we go to the right one from, say, the top number here, then notice how many we're adding. We're adding 1, 2, 3 dots, which is 3 chairs. And if we go to the right one here, we're adding 1, 2, 3 chairs. If we go to the right one, we're adding 1, 2, 3 chairs. And the right one, we're adding 1, 2, 3 chairs. We're adding 1 every time. So if we just look at it in the form here, when we look at our Cartesian graph, when we go to the right one, that means we're increasing one term number, then we're going up by 3 units. And it doesn't matter which term we're on, we always go up by 3 units. And of course, when you do that, what does that do to these dots? Well, that makes them fall exactly in a straight line. These continue on if we had more terms besides the 12 rows. Okay. Now, this is a sequence graph. Okay, so sequences, we don't have a half of a row or 3/4 of a row or 7/8 of a chair. It's whole numbers for both the input and the output, natural numbers actually, and there's not even a 0th row. So there is a first point, which is right here, 1, 5, that's the first row. Then we go to 2, 8, that's the second row. 3, 11, that says in the third row there are 11 chairs. This is the ordered pair 4, 14, so that says in the fourth row we have 14 chairs and so forth. But we do not play connect the dots. However, if we did play the connected dots, what would we get? Well, we would get a solid line. So these points are collinear, meaning there's a single line that contains all the points. But the graph is not the whole line, it's just part of the line. So when we extend this later on in our next section to where we let the domain be all real numbers and not just natural numbers or whole numbers, then we actually get a graph that's a straight line, and of course that's why we call this kind of a function a linear function. When we have a linear function with a domain of the natural numbers or perhaps the whole numbers, then that's called an arithmetic sequence. Or the other way around, if we have an arithmetic sequence and we extend it to letting the domain be all real numbers, then that's called a linear function. And of course it's named after the graph. Okay, so let's go back to our slideshow real fast and kind of review. So this is our task. Start with 5 seats on the first row. Every row has 3 more than the first one, than the one before, I mean. And so this is our arrangement of chairs, and you can count them to see that it works out correctly. So the recursive formula is you start with the first row, n1 equals 5, then we get n sub r equals n sub r minus 1 plus 3. In general, an arithmetic sequence is going to have a formula, recursive formula of the form n1 equals some number, or perhaps n sub 0 equals some number if that's allowed, and then nr equals n sub r minus 1 plus some number m. So the m on the right and this n1 are constants like the 3 and the 5. Okay? And that m is sometimes called the slope. It is the common difference. There's some books will use a d there for common difference, but usually when they extend to linear functions, they'll call it m. So I'm just going to kind of cut to the chase and always use m for this number. And m is just delta n or delta y. It's the difference in the outputs, or the common difference. That is, you take a second y minus a first y. Every time, as long as there's successive y's, you're going to get the same number. And that's why it's called a common difference, and that is delta n or m. So the m, the slope, is constant. So what is the slope? The slope is how much we add each time to the output to get the next output, assuming that we're just going up 1 in the terms, adding 1 to the input. So when we think of a table, we can see that the table is sort of automatic, 1, 2, 3, 4, 5, and so forth for that. And then here's what we came up with for this particular one, and we can see in our table our delta x's are 1. We're going up by 1s on the x's or the r's, the inputs, and the y's or n's, the outputs, are delta y is always 3 because we're always going up by 3. or the common difference is 3. In other words, 8 minus 5 is 3, 11 minus 8 is 3, 14 minus 11 is 3. That's why it's called a difference, because you're subtracting there. So you subtract to find what you add, if that makes sense. So you subtract 1y, or output, minus the previous output. 8 minus 5 is 3. That tells you that you added 3 to 5 to get the 8. And so it's a common amount we're adding each time. So that's a common slope. So we can find a non-recursive pattern for that. And the way we did that is to notice that it's just the initial value plus a bunch of the slopes over and over again. And so the number in parentheses in this case is 1 less than the row number. So it turns out to be input minus 1 is the number of slopes that we add. So it's input minus 1 times the slope plus the initial value at n1. If you set it up at n sub 0 instead, then it's a little bit easier. In fact, it's just n sub r is the slope times r plus n sub 0. So you have r slopes added to the 0th element. In a dynagraph, going over by the same, you go up by 1 here on the inputs, and we're going up by the same amount each time. In this case, 3 on the outputs. Here we have the same chairs stacked up instead of in a circular or semicircular arrangement, and maybe it's a little bit easier here to see that each time when we go from one to the next, we're just adding the same amount. We're adding 3 each time. And of course, if we just keep the top dots, that is a Cartesian coordinate graph. Okay, so it's a sequence graph, and so we have these dots. We're going, the right one is delta n, which is 1, and every time we're going up 3. Right 1 up 3, right 1 up 3, right 1 up 3, right 1 up 3. And so the fact that it's the same every time says that our slope is constant, and that's exactly what makes this straight. And so we get those dots in a straight line. So notice we've looked at a physical representation, a table, recursive formula, non-recursive formula, graphs, and dynagraphs for this particular task. We're going to stop this video now. We'll come back and do this again, the same basic setup that we just did. We'll do it for another example where we're arranging some blocks in the second part.